In the swirling dance of a hurricane, the delicate unfurling of a fern, and the unpredictable tumble of dice across a table, there exists a profound truth that has captivated scientists for generations. Chaos, seemingly random and disordered, might actually represent the universe's most sophisticated form of order. Consider for a moment the weather. Despite centuries of scientific advancement and supercomputers that can perform trillions of calculations per second, meteorologists still cannot predict with absolute certainty what the weather will be like 2 weeks from now. This is not due to a lack of effort or inadequate technology, but rather because weather is a chaotic system, sensitive to initial conditions and governed by nonlinear dynamics that amplify tiny variations into dramatically different outcomes. This phenomenon was famously described by mathematician and meteorologist Edward Lorenz in 1963. While running weather simulations on an early computer, Lorenz discovered that minuscule differences in initial values led to vastly different weather patterns in his model. This led to his famous question: does the flap of a butterfly's wings in Brazil set off a tornado in Texas? The concept, later known as the butterfly effect, became the cornerstone of chaos theory, a scientific framework that reveals how apparent randomness often masks an underlying order of extraordinary complexity. But chaos is not merely a mathematical curiosity or a meteorological phenomenon. It permeates every aspect of our universe, from the turbulent flow of fluids and the erratic orbits of celestial bodies to the irregular beating of a human heart and the intricate patterns of brain activity that constitute consciousness itself. In each case, what appears disordered at first glance reveals itself, upon closer inspection, to be a system of remarkable intricacy and hidden structure. The implications of this revelation extend far beyond academic interest. Understanding chaos has revolutionized fields ranging from ecology and economics to medicine and engineering. It has provided us with new tools to predict stock market fluctuations, model climate change, treat cardiac arrhythmias, and design more efficient technologies. Perhaps most profoundly, it has transformed our philosophical understanding of determinism, predictability, and the very nature of order itself. As we journey deeper into the heart of chaos, we discover that the universe is not a clockwork mechanism of perfect predictability, nor is it a random assemblage of disconnected events. Rather, it exists in a fascinating middle ground, a realm where simple rules give rise to infinite complexity, where boundaries between disciplines dissolve, and where the most profound insights often emerge from what initially appears to be disorder. Our exploration begins with a simple question that has profound implications. What if chaos is not the enemy of order, but its ultimate expression? The roots of chaos theory stretch back to the late 19th century, when French mathematician Henri Poincaré was studying the three-body problem in celestial mechanics. Unlike the two-body problem, which can be solved precisely using Newton's laws of motion, the three-body problem, predicting the motion of three celestial bodies interacting through gravitational attraction, proved stubbornly resistant to exact solution. In 1890, Poincaré discovered that even small uncertainties in the initial positions of the bodies could lead to radically different trajectories over time. This sensitivity to initial conditions became a defining characteristic of chaotic systems. Poincaré wrote, "It may happen that small differences in the initial conditions produce very great ones in the final phenomena. Prediction becomes impossible." This insight lay relatively dormant for decades until Edward Lorenz's groundbreaking work in the 1960s. Working at the Massachusetts Institute of Technology, Lorenz was using a primitive computer to simulate weather patterns using 12 variables and a set of differential equations. One day in 1961, he decided to rerun a simulation, but instead of entering the full 6 decimal place number 0.506127, he rounded it to 0.506. To his astonishment, this tiny discrepancy, equivalent to a gentle breeze, resulted in a completely different weather pattern in his model. Lorenz published his findings in 1963 in a paper titled Deterministic Non-Periodic Flow, which is now considered the founding document of chaos theory. In it, he demonstrated that deterministic systems, those governed by precise mathematical rules without random elements, could nevertheless produce behavior that appeared random and unpredictable. The implications were revolutionary. Classical physics, following Newton and Laplace, had embraced the idea that the universe was essentially deterministic. If we knew the precise position and momentum of every particle, we could, in principle, calculate the entire future and past of the universe. Lorentz's work revealed a fundamental limitation to this view. Even in deterministic systems, long-term prediction might be practically impossible due to our inability to measure initial conditions with infinite precision. Benoit Mandelbrot, a mathematician at IBM, made another crucial contribution to chaos theory in the 1970s with his work on fractals, geometric shapes that exhibit self-similarity at different scales. Fractals provide a visual representation of chaos, demonstrating how simple mathematical rules can generate structures of infinite complexity. The Mandelbrot set, a fractal boundary in the complex plane, has become an iconic image of chaos theory, showing how mathematical beauty can emerge from seemingly simple equations. The term chaos theory itself was coined by mathematician James Yorke in his 1975 paper, Period 3 Implies Chaos. Yorke proved that in certain mathematical systems, the presence of a period 3 orbit implies the existence of orbits of all other periods, as well as completely chaotic orbits. This established a rigorous mathematical foundation for chaos and demonstrated how order and disorder could coexist within the same system. By the 1980s, chaos theory had expanded beyond mathematics and meteorology to influence disciplines ranging from ecology and economics to physics and philosophy. The science of chaos revealed that the boundary between order and disorder was not a sharp line but a rich, complex frontier, a revelation that would transform our understanding of nature's fundamental workings. One of the most captivating aspects of chaos is its visual manifestation. When scientists began to map chaotic systems, they discovered structures of astonishing beauty and complexity. The Lorentz attractor, for instance, resembles a butterfly's wings, a fitting emblem for the butterfly effect. This three-dimensional structure represents all possible states of the Lorentz weather model, showing how the system never exactly repeats itself yet remains within a bounded region of possibility. Similarly, when researchers map the behavior of double pendulums, simple mechanical systems consisting of one pendulum attached to another, they reveal patterns that appear random in time but create distinct structures in phase space. These strange attractors, as they are called, represent the long-term behavior of chaotic systems, islands of pattern within seas of apparent randomness. Perhaps nowhere is the visual beauty of chaos more evident than in fractals. The Mandelbrot set reveals infinite complexity as one zooms in on its boundary, with elaborate spiral and filamentary structures repeating at every scale. Koch snowflakes, Sierpinski triangles, and Julia sets similarly demonstrate how simple iterative processes can generate endless intricacy. What makes these patterns particularly significant is their prevalence in nature. The branching patterns of rivers, trees, and blood vessels, the intricate structures of snowflakes and frost patterns, the spiraling formation of galaxies, hurricanes, and nautilus shells, all exhibit fractal-like properties. Nature, it seems, employs chaos and fractality not as accidents but as fundamental design principles. This observation has profound implications for how we understand the natural world. Rather than seeing chaos as an obstacle to comprehension, we can recognize it as nature's solution to complex problems, a way of generating infinite variation from finite rules, of balancing order and adaptability, of creating systems that are simultaneously robust and flexible. The human heart beats approximately 100,000 times per day, but these beats are not perfectly regular. Even in healthy individuals, there are subtle variations in the time between heartbeats, a phenomenon known as heart rate variability. For many years, medical researchers viewed these variations as random noise in an otherwise orderly system. However, in the 1980s, scientists including Ari Goldberger at Harvard Medical School made a startling discovery. The variations in heart rate are not random but chaotic, following patterns that can be analyzed using the mathematics of chaos theory. More surprisingly, they found that a healthy heart exhibits greater chaotic variability than a diseased one. Hearts with congestive failure or other pathologies often show abnormally regular beating patterns. This insight revolutionized cardiac medicine. Researchers developed new diagnostic tools based on chaos theory to detect early signs of heart disease by identifying abnormal reductions in heart rate complexity. The finding also challenged the fundamental assumption that biological systems should strive for perfect regularity. Instead, it suggested that chaotic variability might be essential for health, allowing the cardiovascular system to adapt quickly to changing demands and environmental conditions. Similar principles apply to the brain. Electroencephalogram, e.g., recordings of neural activity, reveal chaotic patterns that vary with mental states. Consciousness itself appears to exist at the border between order and disorder, a state sometimes called criticality or the edge of chaos. In this state, neural systems maintain a delicate balance. Too much order would make the brain rigid and unresponsive, while too much disorder would render it incapable of coherent thought or memory. Neurologist Walter Freeman of the University of California, Berkeley, demonstrated in the 1990s that when animals perceive a familiar scent, their brain activity temporarily shifts from chaotic to ordered patterns before returning to chaos. This suggests that the brain uses chaos as a background state from which specific, ordered responses can emerge when needed, a form of dynamic stability that combines reliability with adaptability. Even the immune system exhibits chaotic dynamics. The constant production and selection of antibodies creates a system that can respond to virtually any pathogen without needing to anticipate specific threats. This controlled chaos allows biological systems to solve problems that would be impossible to address through rigid, predetermined responses. In each of these cases, chaos serves not as a flaw but as a feature, a sophisticated regulatory mechanism that enhances biological resilience and adaptability. As Nobel laureate Ilya Prigogine observed, living systems exist far from equilibrium, using energy flows to maintain complex, dynamic states that would be impossible in closed equilibrium systems. Chaos, in this view, is not the antithesis of life but one of its essential characteristics. Beyond individual organisms, chaos shapes the dynamics of entire ecosystems. Population biologists Robert May and George Sugihara demonstrated in the 1970s that simple models of population growth can produce chaotic dynamics when growth rates exceed certain thresholds. This explained why some animal populations fluctuate unpredictably despite being governed by deterministic factors like birth rates, death rates, and resource availability. The implications extend to evolutionary theory itself. The traditional view of evolution as a gradual, continuous process has been challenged by the concept of punctuated equilibrium, proposed by paleontologists Niles Eldredge and Stephen Jay Gould in 1972. This theory suggests that species typically experience long periods of stability interrupted by brief bursts of rapid change, a pattern consistent with chaotic dynamics in complex systems. Even more fundamentally, chaos theory helps explain how complex, ordered structures can emerge spontaneously from simple rules without central coordination. This process, known as self-organization, accounts for phenomena ranging from the formation of snowflakes and the hexagonal cells of a beehive to the spiral patterns in sunflower seeds and the synchronized flashing of fireflies. In 1952, mathematician Alan Turing published The Chemical Basis of Morphogenesis, showing how complex patterns could emerge from the interaction of just two chemicals diffusing through tissue. This mechanism explains how leopards get their spots, zebras their stripes, and human embryos develop from single cells into complex organisms with differentiated tissues and organs. The elegant simplicity of Turing's model revealed how local chemical interactions could generate global biological order without a blueprint or central control. Similarly, when Craig Reynolds created computer simulations of flocking behavior in 1986, He discovered that lifelike flocks emerged from just 3 simple rules governing each bird's movement relative to its neighbors. No leader or global coordination was required. Complex, adaptive behavior arose spontaneously from local interactions. These examples illustrate a profound principle. In nature, complexity often emerges not from top-down design but from bottom-up self-organization. Order does not require an orderer. It can arise spontaneously from the chaotic interactions of simpler components following simple rules. Our journey now takes us to the grandest scales, the cosmos itself, where chaos plays a crucial role in the formation and evolution of planetary systems, stars, and galaxies. The solar system, once viewed as the epitome of clockwork regularity, reveals chaotic dynamics under closer examination. In 1989, astronomer Jacques Lasker of the Paris Observatory discovered that the orbits of the planets, particularly the inner planets, show chaotic behavior over long timescales. His calculations indicated that it is impossible to predict Mercury's precise position more than 100 million years into the future. A remarkable finding given the deterministic nature of gravitational physics. This chaotic behavior has profound implications for planetary evolution. The axial tilt of Mars, for instance, can vary chaotically between 0 and 60 degrees over millions of years, compared to Earth's relatively stable tilt of about 23.5 degrees. Earth's stability is largely due to the presence of our unusually large moon, which acts as a gravitational stabilizer. Without this stabilizing influence, Earth's climate would experience extreme variations, potentially making complex life impossible. The formation of planetary systems involves chaotic processes as well. Computer simulations by astronomers like Hal Levison and Alessandro Morbidelli have shown that the early solar system likely experienced a period of dynamic instability that dramatically rearranged the planet's orbits. This NICE model, named after the French city where it was developed, explains peculiarities in our solar system, including the current orbits of the giant planets and the characteristics of the Kuiper belt. On larger scales, the spiral structure of galaxies emerges from chaotic interactions between stars, gas, and dark matter. Density waves propagate through galactic disks, triggering star formation and creating the distinctive spiral arms we observe. These patterns represent another example of self-organization, order emerging from the collective behavior of billions of individual components without centralized control. Even the distribution of galaxies throughout the universe follows patterns reminiscent of fractals and chaotic systems. Galaxies are arranged in vast filaments and sheets surrounding immense voids, a cosmic web whose structure emerges from the interplay between gravity and the expansion of space-time. Cosmologists like John Inasto and Brent Tully have mapped these structures, revealing how the largest observable patterns in the universe arise from the amplification of quantum fluctuations in the early universe, minute variations magnified by gravitational instabilities over cosmic timescales. This cosmic perspective offers a humbling insight. The same principles that govern the beating of our hearts and the branching of trees also shape the structure of the universe itself. Chaos, far from being a mere curiosity, appears to be a fundamental organizing principle at all scales of nature. The realm of quantum physics might seem far removed from chaos theory. After all, quantum mechanics deals with probabilities and wave functions, while chaos theory addresses deterministic systems with unpredictable outcomes. Yet these two foundational frameworks of modern physics intersect in fascinating ways that continue to challenge our understanding of reality. Quantum mechanics, developed in the early 20th century by physicists including Max Planck, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, revealed that at the subatomic scale, nature behaves according to probabilistic rather than deterministic rules. The Heisenberg uncertainty principle, formulated in 1927, establishes that we cannot simultaneously measure a particle's position and momentum with perfect precision, not because of technological limitations, but because these properties do not have precisely defined values simultaneously. This inherent uncertainty seems to preclude the sensitivity to initial conditions that characterizes classical chaotic systems. If initial conditions cannot be precisely defined due to quantum uncertainty, how can we meaningfully discuss their amplification over time? This question led to the development of quantum chaos, a field exploring how quantum systems whose classical counterparts would be chaotic actually behave. Pioneering work by physicists including Martin Gutzwiller in the 1970s revealed that quantum systems retain certain signatures of classical chaos, particularly in the statistical properties of their energy levels. One particularly striking result emerged from studies of quantum billiards, idealized systems where quantum particles are confined to two-dimensional regions of various shapes. Researchers found that in chaotically shaped billiards, the statistical distribution of energy levels follows patterns predicted by random matrix theory, a mathematical framework originally developed to describe the energy levels of complex atomic nuclei. This connection between quantum chaos and random matrix theory has profound implications. It suggests that certain properties of quantum systems are universal, depending not on the specific details of the system, but on general characteristics like symmetry and the presence or absence of chaos in the classical limit. Similar patterns appear in systems as diverse as atomic nuclei, quantum dots, and acoustic resonances. Another example of how seemingly unrelated phenomena follow common mathematical principles. Even more intriguingly, quantum chaos may help explain the emergence of classical chaos from the quantum realm. The process of decoherence, how quantum systems lose their quantum coherence through interaction with their environment, provides a bridge between quantum and classical behavior. Theoretical physicists like Wojciech have shown how chaotic dynamics can accelerate decoherence, helping to explain why macroscopic objects behave classically despite being composed of quantum particles. These investigations reveal that the boundary between quantum and classical physics, like the boundary between order and chaos, is not sharp but represents a rich transitional zone where some of the most fascinating phenomena in nature occur. Our technological world depends increasingly on harnessing chaos rather than suppressing it. From secure communications to efficient energy harvesting, chaos provides solutions to problems that traditional approaches cannot address. In cryptography, chaotic systems offer powerful tools for secure communication. Traditional encryption methods often rely on mathematical problems that are computationally difficult to solve, such as factoring large numbers. Chaos-based cryptography takes a different approach, using the unpredictability of chaotic systems to generate encryption keys and algorithms that are extremely sensitive to initial conditions. For example, in the 1990s, Kevin Cuomo and Alan Oppenheim at MIT demonstrated a secure communication system based on chaotic synchronization. By synchronizing chaotic circuits between sender and receiver, they created a system where the message could be recovered only by a receiver with precisely matching parameters, a form of encryption naturally resistant to eavesdropping. In engineering, chaos theory has transformed how we approach complex systems. Traditional engineering aimed to eliminate unpredictability, treating nonlinearity and chaos as problems to be overcome. Modern approaches increasingly recognize chaos as a feature to be utilized rather than a bug to be eliminated. Control engineers have developed techniques to stabilize chaotic systems using minimal interventions. In 1990, physicists Edward Ott, Celso Grbogy, and James York introduced the OGY method, demonstrating how tiny, precisely timed adjustments could stabilize a chaotic system on any desired trajectory. This approach requires far less energy than traditional control methods, finding applications in stabilizing lasers, controlling chemical reactions, and even regulating cardiac rhythms. In energy harvesting, chaos offers remarkable advantages. Traditional energy collection from vibrations, for instance, works efficiently only at specific frequencies. Chaotic energy harvesters, in contrast, can capture energy across a broad spectrum of frequencies, an essential feature for extracting energy from natural sources like ocean waves or human motion, which rarely oscillate with perfect regularity. Even in artificial intelligence and computing, chaos provides inspiration. Neural networks with chaotic dynamics can solve certain problems more efficiently than traditional architectures. These systems leverage the edge of chaos state to balance exploration of new possibilities with exploitation of known solutions, a property essential for learning in complex environments. Perhaps most significantly, chaos theory has transformed how we approach prediction and forecasting. Traditional forecasting assumed that more data and more powerful computers would inevitably lead to better predictions. Chaos theory revealed the fundamental limitations of this approach for certain systems, leading to the development of ensemble forecasting, a technique that runs multiple simulations with slightly different initial conditions to determine the range of possible outcomes and their probabilities. This method, pioneered by meteorologist Edward Epstein in the 1960s and further developed by researchers like Tim Palmer at the European Center for Medium-Range Weather Forecasts, revolutionized weather prediction. Rather than providing a single forecast that becomes increasingly inaccurate over time, modern weather models produce probability distributions that acknowledge the inherent uncertainties in chaotic systems. The techniques developed for weather prediction have spread to other fields, including economics, epidemiology, and climate science, enabling more realistic assessments of future scenarios and their uncertainties. This represents a profound shift in how we approach prediction, from the illusory goal of perfect deterministic forecasts to probabilistic projections that honestly reflect the limits of predictability. Beyond its scientific and technological implications, chaos theory offers profound philosophical insights that challenge our most fundamental assumptions about order, causality, and the nature of reality itself. The emergence of complexity from simple rules suggests a radically different understanding of order than the one that dominated Western thought for centuries. Since at least the time of Plato, order has been conceptualized as regular, predictable, and often hierarchical, epitomized by perfect geometric forms and celestial motions. Disorder was viewed as a deviation from this ideal state, a falling away from perfection into randomness and unpredictability. Chaos theory inverts this relationship. It reveals that the most sophisticated forms of order may be those that appear, superficially, to be disordered. The infinite complexity of a fractal boundary or a strange attractor represents not a degradation of order but its highest expression, what we might call deep order, visible only when we look beyond surface appearances to underlying patterns and processes. This insight resonates with Eastern philosophical traditions that have long emphasized the unity of apparent opposites. The Chinese concept of yin and yang, for instance, portrays order and chaos not as antagonistic forces, but as complementary aspects of a unified whole, each containing the seed of the other. Similarly, the Taoist emphasis on spontaneous natural order, Ziren, arising without external imposition aligns remarkably well with modern concepts of self-organization and emergence. Chaos theory also challenges our understanding of causality. The linear, mechanistic causality inherited from Newton and Descartes assumes proportionality between cause and effect. Small causes produce small effects, large causes produce large effects. The butterfly effect demolishes this assumption, showing how tiny variations can cascade into massive differences through nonlinear dynamics. This insight has profound implications for historical analysis, economic theory, and even our personal understanding of life choices. In complex systems, the most significant turning points may not be dramatic events but subtle shifts that are amplified through feedback loops and interactions. This suggests a more nuanced approach to causality that recognizes both the role of contingency and the presence of patterns in complex systems. Perhaps most fundamentally, chaos theory challenges the dichotomy between determinism and randomness that has structured scientific and philosophical debate since the Enlightenment. Classical determinism, epitomized by Laplace's demon, a hypothetical intelligence that could predict the entire future of the universe from complete knowledge of its current state, suggested that unpredictability was merely a product of our ignorance rather than an intrinsic feature of reality. Quantum mechanics challenged this view from one direction, introducing fundamental uncertainty at the subatomic level. Chaos theory challenges it from another, showing that even in deterministic systems governed by precise mathematical laws, long-term prediction may be impossible due to sensitivity to initial conditions. Together, these frameworks suggest a universe that is neither purely deterministic nor purely random, but complex in ways that transcend this dichotomy. This realization has prompted philosophers like Ilya Prigogine to propose a third way between determinism and randomness, a perspective that acknowledges both the role of physical laws and the emergence of genuine novelty in complex systems far from equilibrium. In this view, the future is neither completely determined nor completely open, but constrained and channeled by underlying patterns while remaining fundamentally creative and unpredictable in detail. Such insights have implications not only for science but for how we understand ourselves and our place in the cosmos. They suggest that human creativity, consciousness, and free will need not be illusions in a deterministic universe, nor merely random processes without meaning or direction. Instead, they may represent emergent properties of complex systems that are simultaneously bound by physical laws and capable of generating genuine novelty and choice. The story of chaos is still unfolding. New frontiers of research continue to reveal how chaos and complexity shape our world and our understanding of it. In climate science, chaos theory has transformed our approach to modeling and prediction. The climate system exhibits chaotic behavior on multiple timescales, from daily weather patterns to long-term climate oscillations like El Niño Southern Oscillation, ENSO. This chaotic nature explains why climate models produce ranges of possible outcomes rather than single predictions, and why small changes in atmospheric composition can potentially trigger large shifts in climate patterns through feedback mechanisms. Scientists like Tim Palmer at Oxford University are developing new mathematical approaches to climate modeling that explicitly incorporate chaos theory. These models aim not to predict exactly what will happen decades from now, but to identify the range of possible scenarios, their relative likelihoods, and potential tipping points where gradual changes might trigger sudden, dramatic shifts in climate systems. In neuroscience, researchers are exploring how chaotic dynamics contribute to cognition, consciousness, and mental health. Evidence suggests that the brain operates near a critical state between order and disorder, a condition that maximizes information processing capacity, memory, and adaptability. Alterations in these dynamics may underlie conditions ranging from epilepsy and Parkinson's disease to schizophrenia and depression. Carl Friston's free energy principle proposes that the brain functions as a prediction machine that constantly attempts to minimize surprise by updating its internal models of the world. This framework, which has gained significant traction in cognitive neuroscience, incorporates concepts from chaos theory, information theory, and thermodynamics to explain how neural systems self-organize to efficiently represent and respond to their environment. In ecology, chaos theory is helping us understand and manage complex ecosystems. Traditional approaches often assumed that ecosystems tend toward stable equilibrium states, with disturbances viewed as external disruptions. Modern ecological theory recognizes that many ecosystems naturally exhibit chaotic or near-chaotic dynamics, with disturbances playing essential roles in maintaining biodiversity and resilience. This perspective has practical implications for conservation and resource management. Instead of trying to maintain ecosystems in fixed states, adaptive management approaches work with natural variability and focus on maintaining the conditions that allow ecosystems to self-regulate and adapt to changing conditions. This might involve maintaining habitat connectivity, protecting keystone species, or even allowing controlled burns in forest ecosystems that have evolved with fire as a natural disturbance regime. In computer science and artificial intelligence, chaos and complexity theory are inspiring new approaches to machine learning and computation. Reservoir computing, for instance, uses the intrinsic dynamics of chaotic systems to process information, an approach that can solve certain problems more efficiently than traditional computing methods. Similarly, evolutionary algorithms that incorporate principles of self-organization and selection have proven effective for solving complex optimization problems that resist analytical solutions. Perhaps the most exciting frontier lies in the emerging science of complexity itself, an interdisciplinary field exploring how interactions between parts give rise to collective behaviors and properties not evident in the parts themselves. The Santa Fe Institute, founded in 1984 by scientists including Nobel laureates Murray Gell-Mann and Kenneth Arrow, has pioneered this approach, bringing together researchers from physics, biology, economics, computer science, and other disciplines to develop common theoretical frameworks for understanding complex adaptive systems. This work is revealing deep connections between seemingly disparate phenomena: how cities grow, how economies evolve, how innovations spread, and how civilizations rise and fall. By identifying common patterns and principles across different domains, complexity science offers the possibility of a more unified understanding of our world and our place within it. As our journey through the science of chaos comes to a close, we return to our initial question. What if chaos is not the enemy of order, but its ultimate expression? The evidence we have explored, from the beating of a human heart to the formation of galaxies, from the patterns of weather to the dynamics of quantum systems, suggests a profound revision of how we understand order itself. Rather than seeing order and disorder as opposites, we might better view them as complementary aspects of a deeper principle: complexity. In this view, the most interesting and generative systems in nature exist not in states of perfect regularity or complete randomness, but in the rich territory between these extremes, the realm of complex, adaptive, self-organizing systems that combine stability with flexibility, predictability with surprise, conservation with innovation. This perspective invites us to reconsider our cultural and psychological associations with chaos. Throughout history, chaos has often been portrayed as a negative force, something to be feared, controlled, or eliminated. From the primordial chaos of ancient creation myths to modern anxieties about social disorder, we have tended to equate chaos with destruction and suffering. Yet the science of chaos reveals a more nuanced reality. What appears as chaos from one perspective may reveal itself as complex order from another. What seems like disorder at one scale may be an essential component of order at a larger scale. The turbulence that disrupts the flow of a river also oxygenates the water that sustains aquatic life. The forest fire that destroys individual trees rejuvenates the ecosystem as a whole. The economic disruption that displaces workers in one industry creates opportunities for innovation in another. This is not to minimize the real suffering that can accompany disorder and upheaval, but to suggest that our instinctive aversion to chaos might sometimes blind us to its creative potential. The science of chaos invites us to cultivate a more balanced relationship with uncertainty, complexity, and change, to see them not merely as threats to be eliminated, but as fundamental features of a dynamic universe that make life, intelligence, and evolution possible. Perhaps most profoundly, chaos theory offers a new metaphor for understanding our place in the cosmos. The deterministic worldview that emerged from classical physics often portrayed the universe as a vast machine grinding inexorably toward a predetermined future. The purely probabilistic interpretation of quantum mechanics sometimes seemed to reduce reality to random fluctuations without pattern or purpose. Neither view left much room for genuine creativity, meaning, or agency. The science of chaos and complexity suggests an alternative vision. A universe of emergent order, where simple rules generate infinite complexity, where determination and chance intertwine in ways that leave room for novelty and choice, where the future is neither completely fixed nor completely random but creatively constrained, influenced by the past without being entirely determined by it. In such a universe, order is not imposed from above but emerges from within. Pattern and structure are not signs of external design but natural expressions of how complex systems organize themselves. And chaos, far from being a flaw in creation or a sign of its absence, represents the universe's most sophisticated form of order, the wellspring of its boundless creativity and endless capacity for surprise. This perspective does not provide easy answers to age-old questions about purpose and meaning, but it does suggest that the capacity for self-organization, complexity, and emergence that we observe throughout nature is not incidental but fundamental, not a bizarre exception to cosmic order but one of its deepest expressions. As we contemplate the swirling clouds of a distant nebula, the intricate patterns of a coral reef, or the firing of billions of neurons that constitutes a single human thought, we might see not merely physical processes governed by impersonal laws, but manifestations of a universe in which complexity, creativity, and the emergence of novelty are built into the very fabric of reality. In this light, chaos appears not as the universe's greatest mistake, but as its greatest achievement, the principle that transforms simple physical laws into the infinite diversity and complexity of the world we inhabit. Far from being the absence of order, chaos might indeed be the universe's greatest order, not the order of the machine with its perfect regularity and predictability, but the order of life itself with its boundless capacity for adaptation, innovation, and surprise. This recognition invites us to approach the world with renewed humility and wonder, to see in apparent disorder the hidden patterns that connect us to the cosmos, and to find in complexity not an obstacle to understanding but a gateway to deeper appreciation of nature's endless creativity. In embracing chaos as order, we might discover not only new scientific insights, but a more profound and accurate vision of our place in the creative unfolding of the universe itself.